Now we move on to Lagrange's equations and a different approach to problem solving in physics. So the last chapter that we covered, chapter 6, may have seemed rather esoteric because it was a bunch of math. Now we're going to talk about how we apply that. Now, there are some advantages over Newton's laws. You can solve most of the same problems as long as you neglect friction and non-conservative forces. But Lagrange's equations take the same form for any coordinate system. So whether you are working with spherical polar coordinates or Cartesian coordinates, you're working with the same thing all the time. And we don't need to have constraint equations. You don't need to necessarily consider the tension in the string if you're not after the tension in the string, although we'll get to how you can do that later. So in that sense, they are a lot more general. They're also applicable in areas outside of classical mechanics. They can be deceptively easy to work with and to solve problems with, and sometimes that can hide the physics. And just because you can get the equations, the same equations you would get with Newton's laws, perhaps a little bit easier, that doesn't mean that solving those equations is easy. You can often set the equations up really easily, but making sense of them is still hard. So we are going to start by defining the Lagrangian. We will start with expressing the kinetic energy as 1/2 m x dot squared plus y dot squared plus z dot squared. And that's the kinetic energy. And the potential energy, we will simply say that this is a function of position. So this is leaving us with conservative forces only. So this is going to be u as a function of x, y, and z. Now, when we were working in the previous chapter, we allowed some explicit time dependence. Here, we are explicitly not allowing time dependence. So we will then define the Lagrangian as t minus u. There is no simple explanation for why we're making this definition. And Taylor doesn't even address it, which means it's gnarly and ugly. So take me at my word. We're introducing this term. And then we can say that partial L, partial X, at least if we have a one-dimensional force, is then negative partial U, partial X, which is equal to the X component of the force. And partial L, partial X dot gives us 2mx dot times 2. So mx dot. This is equal to the momentum in the x direction. And then we can apply the Euler-Lagrange equations, and this says that partial L partial x is equal to d dt of partial L partial x dot. And using these two definitions, this just tells us that fx is equal to px dot, or dpx dt. So this is then, at least for the x dimension, this x direction, this is equivalent to Newton's laws. We can then write all three dimensions. Fx equals mx double dot, Fy equals my double dot, Fz equals mz double dot. Okay, and then we will introduce Hamilton's principle, which defines the action. So here we are explicitly defining S to be the action. It is the integral of the Lagrangian as a function of time. And Hamilton's principle says that the actual path is that which makes the action stationary. So then we have three equivalent statements: that a particle's path is determined by Newton's laws, that its path is determined by Lagrange's equations, and that its path is determined by Hamilton's principle. So all three are saying the same thing. So we are coming up with an equivalent way of describing the equations of motions, equivalent to what you had when you were working with Newton's equations, and we will see that this is actually quite useful. Now, instead of using Cartesian coordinates, we introduced at the end of the last chapter that we can actually describe this in terms of any coordinates. So we can use any other coordinates, for example, spherical polar coordinates, and we assume that if we're talking about one particle's motion in 3 dimensions, so we will have then 3 different QI. I'm starting at 1 because the book does, but I'd rather start at 0. We have 3 different unique QI for determining R exactly. We can write R as a function of these QI. Keep in the back of your head that an example of this is spherical polar coordinates. You can always describe the position in terms of spherical polar coordinates. And then you can write the Lagrangian as a function of QI and QI dot. So, I would like to introduce the notation where we assume that there are all 3 subscripts, even though I'm being a lazy physicist and only writing 1. So this is explicitly including all 3 dimensions. And here I've dropped the explicit time dependence because we're not going to use it. We're considering only cases where the Lagrangian does not have explicit time dependence. All right, and then with that, we can then have Lagrange's equations, just applying the Lagrange-Euler equation to our generalized coordinates and this new thing we introduced called the Lagrangian. So this is just a special case of the Lagrange-Euler equations. I'm going to skip example 7.1 because it is redundant. We will then, so here we talked about the force and the momentum. For Cartesian coordinates, we are going to define the generalized force as partial L, partial QI. So when the generalized coordinates have a dimension of length, this will have units of force, but for instance, if you have an angle, this has units of torque instead. So the Lagrangian has units of energy. So if you divide by distance, you end up with a unit of force. And if you multiply a force times a distance, you have a torque, so that the torque has the same units as the units of energy. But we're going to have this concept of a generalized force where it no longer matters if the things that we're talking about are actually distances here. The QI do not have to be distances. They can be any coordinate. And we introduce the concept of a generalized momentum, so directly analogous to this. If the QI are a distance, the generalized momentum has a unit of momentum, but if it is not, it can in principle have different units. So then our Lagrange equations say that the generalized force is equal to the time derivative of the generalized momentum. All right, so now we're going to take that and look at what that means for a particle in 2 dimensions. This is example 7.2. And we will see that the equations of motion for a particle in 2 dimensions in polar coordinates fall out rather easily. Whereas when we had to derive them in Newtonian mechanics, it was kind of ugly and complicated. So we will start by saying that we're going to write the velocity in terms of the radial velocity, which is just r dot, and the tangential velocity, which is in what we call the theta hat direction, which is phi hat, which is r phi dot. And this means that our kinetic energy is 1/2 m r dot squared plus r squared phi dot squared. And then our Lagrangian, we are going to leave our potential energy as just a function of r and phi. Our Lagrangian is just then m r phi dot squared looking at the wrong line, 1/2 m r dot squared plus r squared phi dot squared minus u of r and phi. Now, partial L partial r is equal to negative partial u partial r. That's from this term. And then plus m r phi dot squared. And we will call this F sub r because it is the radial component of the force. This then, through Lagrange's equations, has to equal d dt partial L partial r dot and partial, so this is d dt of 2 times m times 2r dot. So we have m r dot. So this is m r double dot. So our radial component, our radial acceleration is equal to the radial force plus what we previously introduced as the centripetal force, which is this fictitious force that comes from the difference between Cartesian coordinates and spherical polar coordinates. So if you're moving in a system that is moving, you have an apparent centripetal force. If you're moving in a system that is rotating, you have an apparent force that keeps you rotating. Then partial L partial phi is negative partial u partial phi. Now this has units of energy or of force times distance. We will call this r phi dot, and this is equal to the torque due to whatever force is creating this potential. And this is equal to d dt partial L partial phi dot. So this is d dt of m r squared phi dot. Now this is just the angular momentum. So this says that the torque is equal to the time derivative of the angular momentum. Now, you didn't have to express it that way. You didn't have to name it these things. So when we did our analysis in Newtonian mechanics, it took a lot more work, but it perhaps taught us a lot more about the system and about what was going on. Here, the equations of motion fall out rather easily. We didn't have to work very hard for them, but it's easy to see them as equations detached from what is going on physically. We say that these equations appear in their natural form. And I would just like to point out that so here we called this the generalized force. This does not have, in this case, units of force. In this case, it does, because we're looking at the time derivative with respect to something that has units of time. Likewise, the generalized momentum, in this case angular momentum, does not necessarily have units of momentum. And it is also worth pointing out, for any given generalized force, partial L, partial Q, I, if this is equal to 0, then you have something which is conserved. Your partial L, partial QI dot, the generalized momentum, is conserved, or some sort of constants. All right, so now we're going to sketch what happens for several unconstrained particles, and the book doesn't go in a ton of detail. I am going to try to convince you that this is true. So there was nothing in our derivation that said that we had explicitly 3 coordinates. So it just said that you have some generalized coordinates that describe the system. So we can take a system where you have, we'll start with 2 particles, they will be described by positions R1 with velocity R1 dot, R2 with velocity R2 dot, and then in principle we could have Ri with Ri dot. And so then, because we're talking about n particles, and each of these positions has 3 components, then we have 3n generalized coordinates, 3 for each particle. We have generalized forces, Fij, and generalized momenta, Pij. So the Lagrange equations say that the Fij are equal to the Pij dot. I is the particle, and J is the coordinate. So we have 3n of these equations. And they don't have to be positions. They could be any other coordinates. It could be, if you're talking about a solid, for instance, a crystal, you could be describing the distances between the different atoms in the crystal. And then for each of these parameters, you then have L, partial Qij. There's nothing about our derivation that put a limit on the number of different coordinates we could have. This is equal to the time derivative of partial L, partial Qij dot. And so my let's see, my derivation is maybe slightly more compact than that in the book, which is usually not a great sign. We have 1 through 3n of these equations. So as long as, whatever the system is, as long as you can describe it by a bunch of coordinates, then you can write one Euler-Lagrange equation for each coordinate. In this case, we just happen to have indices for each of the particles in each of the coordinates. And no matter what, the Euler-Lagrange equation is true. This is much of theoretical physics these days. You write this down, you try to solve it. You usually can't solve it analytically, so you use clever methods to solve it numerically. Okay, so now we're going to look at an example of a constrained system. Now, at least what we've covered so far, if you have a constrained system, you have to eliminate the constraints so that you have your Lagrangian only in terms of the variables that you need. And that was something that I didn't, when you actually apply this, the form that we have now requires that you use the minimum, the approach that we have now, you have to use the minimum number of coordinates to describe the system. So we will cover a plane pendulum. So that is a pendulum which is constrained to be in the X and Y direction. So there you have something, some object. We will put the origin at the pivot point of the pendulum, and then it is on, so we have the constraint x squared plus y squared equals the length squared. So we only have 1 degree of freedom. We are going to choose the angle phi, and then we will write the velocity as L phi dot. And here, when we get to the potential energy, there's a whole bunch of different ways that you could do this, and I often have some qualms with books where they make it seem like it's immediately obvious. So if you were at the bottom, so first of all, we're going to go with the form mgh, whatever that height is, and then this is going to be mg, and then the length. So here I'm going to make, if we make a triangle here, this is the length L, and then we're going to subtract off this length. So that height is, so L minus, and then this length is L cosine phi, because we are looking at the adjacent component of the triangle. So then we can write our Lagrangian as 1/2 m L squared phi dot squared minus mgl 1 minus cosine phi. Now this term is constant, so all that really matters is that you get the negative phi dependence of the negative cosine phi dependence of the potential energy. You can set your 0 somewhere else. It doesn't matter. All right, then this is our Lagrangian. Partial L partial phi is equal to, here we have negative mgl times negative sign. So this is, oof, that is not legible, is it? My handwriting does not get better with age. All right, then partial L partial phi dot is equal to ml squared phi dot. And because L is fixed when we take the time derivative, this is, so I will do, actually, let me do it my favorite way, using color coding. D, dt, the only thing we take the derivative of is phi dot. So we have negative mgl sine phi equals mgl squared phi double dot. This you can recognize as the torque due to gravity. And this is, let's see, I have an extra I have here G times ml squared. This is my moment of inertia, and this is the angular velocity. So here I have that the torque due to gravity, let's see, I added an erroneous, there we go. The torque due, and this is alpha. So the torque due to gravity is equal to the moment of inertia times the angular acceleration. So we have then, if you remember the way we derive this equation in introductory physics, it's a lot more cumbersome, and it involves complicated analyses of free body diagrams, and you have to add vector forces, and then you have to say, it gets confusing. You have to say, okay, well, the tension cancels out the tangential component, so I'm left with only the component that leads to acceleration in this direction, or sorry, the tension cancels out the radial component. So here it was much faster. It's also a little bit divorced from a physical understanding of what's going on in the system. But often we can go back and use this and reconstruct what was going on in the physical system. All right, so we can talk in general about how we would address constrained coordinate systems. Now, first of all, what do we mean by a constrained coordinate system? What we mean is one where there are fewer than 3n dimensions necessary to describe the system. So when we had the plane pendulum, you have a pendulum fixed in the plane, and it is fixed, it has a fixed length. So then you can describe the system with only one variable as opposed to 3 variables for the position of the mass. In general, if you have any system, you can describe it with n vectors, r, which can depend on time and the generalized variables. So there's 1 through n vectors, r to describe the positions of the particles, and you then have n generalized coordinates, which are functions of the ri and the t. So this is very vague in general. So there are up to 3n of those. We want to choose the smallest number of coordinates to describe the system. And there are ways that you can describe it when you have the equations for the constraint, but otherwise it is at least easier if all we are interested in is figuring out the position as a function of time. We can get that when we write the minimum number of generalized coordinates. So then we can look at the double pendulum, which is in figure 7.3, so I'm going to try to make a quick sketch of it. Fortunately, this is not too tricky. This is an example where you can have a problem that is very complicated to solve in Newtonian mechanics, but it is relatively easy with Lagrangians. So we have one pendulum. We will describe, this has an angle M1, and this, or sorry, phi 1, and this has a mass M1. And then there is a second mass, which is connected on a pivot point to the first one. This has an angle phi 2, and length L2, and mass M2. Oh, and this is L1. So now I've written everything for it. The position, so we are going to be able to describe this with two different angles, phi 1 and phi 2. So we can write R1 is L1 sine phi 1 L1 cosine phi 1. We are not going to bother with the z coordinate because we're fixing this in the x and y plane. R2 is, you can add the sum of these two vectors. So this is L1 sine phi 1 plus L2 sine phi 2. L1 cosine phi 1 plus L2 cosine phi 2. So this is describing R1 solely in terms of phi 1, and this is describing R2 in terms of phi 1, and I will not write that, we'll just say it. It's describing phi R2 in terms of phi 1 and phi 2. So in these coordinates, in these examples, the coordinates didn't depend on time, at least not explicitly. So now we will, this one, if you wanted to solve it, you would have to write the velocity. So you would end up with a phi 1 dot and a cosine and a cosine 1 and a phi 1 and a phi 1 dot, and you would end up with a bunch of sines and cosines and phi 1 dots and phi 2 dots, and it would be a big, long, ugly expression. The kinetic energy would depend on both the angles and on their derivatives as a function of time, and the potential would depend as well on both of the angles. We will leave that as an exercise to the reader, but this is an example of how you can describe it in terms of simply one coordinate, of two coordinates. You also can see what's going on in figure 7.4, now you have a train, and the train is moving, and you have a pendulum on a train. We will say that the acceleration of the train is given. So we have the position of the train is 1/2 AT squared. And then if you want to describe the position of the pendulum, the bob of the pendulum as a function of time is L sine phi plus the x component, and then L cosine phi. So you can describe the position of the pendulum in the reference frame, stationary relative to the Earth, with a Lagrangian. And you would here have an explicit time dependence in the coordinates, but you still don't end up with a time dependence in the potential. So you can solve the problems as written. Now, these concepts of generalized variables and generalized coordinates and how many you need is related to a concept called number of degrees of freedom, which is the number of coordinates which can be independently varied. So here, because we have fixed it into the xy plane and you have two masses, you can describe the entire system with two variables. So we say that it has 2 degrees of freedom. You're fixing the length of each pendulum blob. And then here you have the, when you have the pendulum on the train, you can describe everything because the position of the train is known as a function of time. You can describe the position of the train as a function of all time by simply one variable. Describing it in terms of its x and y positions gets rather complicated, but if you know the angle of the pendulum on the train, you know the position of the train, of the pendulum relative to the Earth everywhere, even if the equations are a little bit ugly. So in general, if you have a free particle, you have 3 degrees of freedom because you can move in x and y and z. And then if you have n particles, you have 3 times n because you have the coordinates for each of the different particles, for each of the 3 coordinates for each different particle. When the number of degrees of freedom is less than 3n, we say that the system is constrained. And if the number of generalized coordinates is equal to the number of degrees of freedom, the system is holonomic. And we're only going to talk about holonomic equations. We're only going to try to solve those. That class of equations, that class of systems is the ones that we can actually describe with the techniques used here. And we leave the other systems for another class, or no classes. If you're a physics major, you're quite likely to never encounter the other types of systems. So an example of a non-holonomic system is a ball rolling around on the floor, because you have, if you want to describe the position of the ball and actually consider more than just its XY position, but where is it? So imagine a globe and you want to know which continent is sitting on the floor at any given time. Then where the position of the globe depends on which path it took to get there. So you could roll this way and then that way, and Africa is touching the ground, but you roll from here to there and you end up with South America touching the ground. So if you wanted to describe that system and get the orientation of the globe as well, you would need 5 coordinates, because here you've constricted it to be on the floor. So you don't have, for the center of mass, you don't have 3 coordinates, you only have 2. But then you would have to describe the orientation of the globe relative to the floor, you would need an additional 3 coordinates. So that is an example of a non-holonomic system, which we are not describing because we can't. This type of approach is not going to work for that. So we will restrict ourselves to cases where we can describe, where the system can be described by a number of variables equal to the number of degrees of freedom. All right, so now we're going to go through a quick and dirty proof of Lagrange's equations with constraints. But I want to say this is very similar to what we did in chapter 6. It's basically the derivation of the Lagrange-Euler equation, but specifically applying it to our definition of a Lagrangian. So it's a bit redundant, but we're going to do it anyways because you got to see something on average for about 10 times in order for it to really stick. We are going to confine ourselves to forces where there is, so forces of constraint like a bead on a wire or a normal force, not necessarily conservative forces, but it doesn't really matter if they are non-conservative. But if they are non-conservative, the form of Lagrange equations in this chapter don't apply. So that's basically a disclaimer saying you don't necessarily have to have conservative forces, but you have to have, but you can't apply this if you have non-conservative forces. We then can also allow non-constraint forces. So what that means is that we are allowing things like gravity, so where there is a potential that exists, we are going to consider a Lagrangian T minus U. So these are conservative forces. We are assuming that the constraints are how you restrict the number of variables. And so then this term only includes conservative forces. Okay, so then the action integral is going to be stationary when we are on the right path. So we are going to parameterize the slightly wrong path as big R plus the right path times epsilon, which is a vector, as a function of time. So this is, just like we did when we covered chapter 6, a slight deviation from, so if this is R, this is capital R, and there's some deviation from that. We force capital R to go through the endpoints. So we're only looking at what is the path between these 2 points. And we have them be, so we're going to assume that these two paths are on some surface, and the epsilon is constrained on the same surface as well. So if you are talking about a particle moving in a plane, you have to stay in the plane. If you say it's in the xy plane, there's no z component, your epsilon cannot have a z component. We're only going to consider deviations that are within those constraints. If you have something that is moving on an angle, you're only going to consider deviations along that path that you are allowed by the constraints. And that really is saying that epsilon at T1 is equal to 0, and epsilon at T2 is also equal to 0. We want a slight change in the action to be 0, so that is S minus S naught. A slight change in the Lagrangian is then the Lagrangian evaluated at R dot, capital R dot, and T minus L of the Lagrangian evaluated at little r dot, and T. And then this is going to be 1/2 M, and then capital R, not the dot, capital R dot, capital R. I have to put the dots in the right spots. And then minus, let's see, this is minus u of capital R and t plus 1/2 m r dot, these should have dots. R dot, big R's, little r's. Then this is a plus u of little r and t. And this we can expand out into r dot dot r dot, and then plus 2 r dot dot epsilon dot plus epsilon dot dot epsilon dot. So we are going to drop this term because this term is of order epsilon squared. So it is a very small change, or epsilon dot squared. So we are assuming that this is negligible. And then we are going to write this term as u of r t, and then I have to be careful. Then I need a plus epsilon. So here I've not folded in the negative sign yet. Plus epsilon dot del u. So here there's a sleight of hand that I kind of don't like, because if you came up through the US system and you took a standard calculus 1, 2, and 3 class, at least as I had it, no one talked to you about multivariable Taylor series, because physicists use it, but the mathematicians don't find it that interesting. It's just the obvious extension of the one-dimensional Taylor series. But we can actually, let me choose a lovely standout color for my aside. We can describe the same way that you can describe a single variable function as a sum of its derivatives. You can describe a multivariable function where there are k different variables as the sum of derivatives, powers of derivatives, mixing different terms. This is admittedly straight off of Wikipedia. Wikipedia is really good for technical subjects because turns out we like putting things on Wikipedia. So here you have the vector minus, so the difference between this term to the alpha over, well, it is in principle, let me put a magnitude there because this is a scalar function. We need to make sure we don't have a vector. This is, you have to make sure that you do not have, so you're keeping fewer terms. Well, you can go to infinitely high terms. Now in practice, what this means is that you can take f of x and y and describe it as f at some, expand it about the point a, b. And then this is partial x. I'm going to just leave f times x minus a plus partial y of x times y minus b plus 1/2 the second derivative with respect to x, x minus a quantity squared. You're going to have a similar term for the y term, y minus b. And then you're going to have the cross derivative term. I think this should be the nth. Let's see, I'm a little confused by the Wikipedia notation I wrote down in my notes. I can tell you what we do. Here you've got a, and here you actually, in your sum, would end up with two terms where you have one derivative relative to x and one relative to y. And here I'm assuming that they're nice and neat and smooth, so I can swap the order of them nicely. I have an x minus a times y minus b. Okay, so I can do this, and the first term, if you look here, turns out to be the difference. This is your epsilon, the displacement from the equilibrium position, dotted with the gradient of u. Voila! So, what I don't like about that, the way that it is covered in the book, is that it is weird and esoteric, and they just say, they just fudge over it. All right, so now I can do that, and then this entire term turns out to be delta L is, let's see, I've got this term canceling. Here I got a sign wrong. This term cancels that term, so I am left with just the difference term, which is m r dot dotted with epsilon dot. And then I am left with, because this had a minus sign in front of it, minus epsilon dotted with the gradient of the potential. Okay, so this guy here is going to leave me with delta S. Here I'm going to use the we use the trick that we did before, and we integrate. So we're given delta S is the integral of m r dot e dot minus epsilon dot grad u dt. I will not go through this because I went through this in the lecture on chapter 6. We can integrate this by parts. There's just 3 different variables instead of just 1. And this term becomes negative epsilon dotted with mr double dot. So you're integrating this by parts, and because the points are fixed on the end, then the integral that is the product of the two functions goes away because epsilon is 0 at the endpoints. And we get that delta S is negative T1, T2, epsilon dot grad u dt. Now, this, so here nope, I have to backtrack just a touch. I'm going to write this as negative T1, T2, epsilon mr double dot plus grad u dt, and this is negative, so our total force is the force from constraints and plus the force del grad, so the force from conservative terms, and the force from conservative terms is this part. So we are just left with T1, T2, and epsilon dot F constraint. But now our constraint forces have to be perpendicular to the surface because they are keeping the thing on the surface. So this entire thing goes to 0. The final section is labeled the final proof. I personally didn't think that this added much over what we did in chapter 6, where we talked about how this applies generally. And it really just does some hand waving and saying, okay, here we showed it more explicitly for one particular set of coordinates for one particle. You could do it instead for generalized coordinates and more than one particle. But at this point, I think I've gone through the proof for Lagrange's equation 3 or 4 times from different angles, and I don't know that it would be particularly enlightening. So instead, we are going to move on to examples. Okay, so now we get to what I think is the most useful section of this chapter, which is examples of Lagrange's equations, because for many purposes, you don't actually need to remember the derivation, you just need to know how to use it. So Lagrangian formalism makes it easy to write down the equations of motion, but I would just like to point out it doesn't necessarily mean that that means that they are easy to solve. Often what you will see is that you get the same equations that you would have gotten using Newton's laws, but they fall out of it much easier. So we're going to do example 7.3. Which is an Atwood machine. And so here we're going to put the center of the pulley here. We are going to define 2 variables. We have we'll call this, we've got one mass here, so it's 2 masses connected by a spring, connected by a string over a pulley. And here we've got mass M1 and M2. This distance we will call Y. We are going to put the 0 for potential energy right here. This distance we are going to call X. And now we actually have an equation of constraint because the length of the string is equal to Y plus X plus, and then this we will call A, pi A. How we're going to use it in this approach later in the chapter, we are going to come back to how you use equations of constraint and you actually can get more information. But for now, we're going to use this to eliminate one of the variables. So our kinetic energy is equal to 1/2 m1 x dot squared plus 1/2 m2 y dot squared and then our potential energy is equal to negative m1 minus m2. Well, actually, let me write it this way. Our potential energy is equal to negative m1 y times g minus m2, let's see, I have, this should be an m2 and this is an m1, x g, and then here's how I'm going to use my equation of constraint. Here I have to, I want to eliminate either x or y, and x dot, either x dot or y dot. And so I am going to use this equation. I can write y equals L minus x minus pi minus a. That also means that y dot is negative x dot. Now what you could do here is that you actually could have looked at the diagram and determined that, but I like doing it this way so that you can see where it comes from, because sometimes when you're going through the textbook it kind of feels a bit like they're looking at some clever trick. This is a protocol that you can use where you always, if you can write your constraint as an equation, you can write down your kinetic and potential energy in terms of the variables that are easier to write it down in terms of, and then move on from there. Okay, so here, this is, so when we get in here, this is where when we're, so for this part, this is easy. So then our kinetic energy is 1/2 m1 plus m2 x dot squared. Here, what we see is when we're plugging this in, the potential energy doesn't quite substitute like, well, here, if we wanted to write it all in terms of x, we have this equation here, so we get negative m1 x g, and then minus m2, and then I'm going to put the x term in one spot because everything else is a constant. So we have pi plus a minus L. I've switched the signs there, which is why that switched signs. I multiplied the negative sign through, and then m to g. Now the book just lumps that in and says that's a constant. It all depends on, how you define which variable. So the thing that matters here is, and I would say the book actually defined y slightly differently because of the shift in the potential energy relative to what the book has. There is an offset there, but the real point is that you have a term which looks like negative m1 minus m2 xg plus some constant. So then our Lagrangian is 1/2 m1 plus m2 times x dot squared minus the potential, so plus m1 minus m2 x g minus u naught. Okay, then we want our Euler-Lagrange equations, which say that partial L partial Q equals the time derivative of partial L partial Q dot. So we're going to take our derivatives. Partial L partial x is equal to m1 minus m2 times g. Partial L partial x dot is equal to m1 plus m2 x dot. And here I'm going to be a little bit lazy. I take the time derivative of this, and instead of rewriting it, I'm switching colors, and I get a dot there. Now, this has to equal that, so I get m1 minus m2 g equals m1 plus m2 x double dot, and this is easily solved to get x double dot equals m1 minus m2 over m1 plus m2 times g. Okay, so if we use Newton's laws in this case, then, and let me actually slip that in over here. If we use Newton's laws, what we would look at the net force, and we would have to say that the net force on 1 is mass 1 times g minus the tension equals m1x double dot. Now, the reason, so here my x is defined as positive when it is pointing down, which is the reason gravity is positive and tension is negative. If I look at the, this, and actually let me just put this as tension 1, because if you had a massive pulley, you would in principle have a difference between the two different pulleys. So here, I would have for the second equation, tension 2 minus m2g equals m2x double dot. So here I have used the fact that y, the derivative of y is the opposite, has the opposite sign of the derivative of x. All right, so here I would have to, when I have no, the pulley is massless, these two tensions are the same, and I can solve this and say T equals m2x double dot plus m2g. Plug this into this equation, and I get m1 plus m1 minus m2 times g minus m2 x double dot equals m1 x double dot. All right, and then I get the same equation. Here I get the x double dot. I'm going to move this guy to the same side. And I get x double dot equals m1 minus m2 over m1 plus m2 times g. Okay, so now we're going to go back and we're going to add mass, and I'm going a little bit beyond the book. I want you to think about this problem from all sorts of ways, and when you add mass, you're going to see why the Lagrangian approach, at least one of the examples of how the Lagrangian approach makes things a little bit simpler. So when we add mass, it is not going to change the potential energy because the pulley is fixed. So when we add mass to the pulley is fixed, so the potential energy doesn't change, but the kinetic energy changes. So now you have plus 1/2 I, the moment of inertia of the pulley, alpha squared, where alpha is, we're going to assume no slipping, so the distance, let's see, the distance, alpha is the angular acceleration, so the radius of the pulley times alpha is equal to, the radius of the pulley times alpha is equal to x dot, so this is the second derivative of the angular change. So here we can write this alpha instead as x dot squared divided by a squared. And then, let me make room. So then our kinetic energy equation just becomes 1/2 m1 plus m2 plus I over a squared, x dot squared, and this becomes 1/2 m1 plus m2 plus I over a squared, x dot squared plus m1 minus m2 x g. Now here, the part that changes is, it doesn't change anything here. We add a plus I over a squared here. And our equation is very similar, but now we get x double dot equals m1 minus m2 over m1 plus m2 plus I over a squared times g. So the addition of the moment of inertia, a non-zero moment of inertia, only made a slight change. It is a quick algebraic equation to solve that. When you approach it through Newton's laws, so you still have these two equations, except that now I have to label these two things differently. So this I'm going to call T1, and this one I'm going to call T2. And I can no longer solve the equation this quickly, and I have to add a third equation because I have to consider the angular motion of the pulley. So I'm going to have the net force on mass 1, the net force on mass 2, and the net torque on the pulley. So because I want to get everything in terms of the derivatives of x, so here I'm going to consider rotations this way to be positive, And that means that T1 acts negative. If T2 is larger, then, let's see, I had that backwards. I want to have this as T1 minus T2 is our net force times A, because here, this torque, I have the radius cross with the force, and that's going to give me a torque that, here I have to be careful because you're seeing the mirror image. Let me not do the cross product. When I want the acceleration to be positive, T1 should be larger, and this is then equal to, so the torque is equal to I alpha, which is equal to I x double dot over A. So now I can write this as T1 minus T2 equals I over A squared x double dot, and then I can take this equation. I want to end up with T1 minus T2, so I'm going to take the negative of this equation and subtract that equation. Or I can take the sum of these. The sum of these two equations gives me T1 minus T2, which is, let's see, T1 minus T2, no, T2 minus T1. T2 minus T1 plus M1 minus M2 G equals M1 plus M2 X double dot. So I flipped the signs here. That's why I was getting so confused. I'm going to flip my 2's and 1's. No, I actually wanted to do that. Now when I add this, the tensions cancel out, and I am left with M1 minus M2 times G equals M1 plus M2 plus I over A squared X double dot, and I get to the same equation that I had up here. So it is slightly easier when you use the Lagrangian approach because you just have to write down the kinetic energy. In the Newton's law approach, you have to write down the net force for each of the two masses and the net torque for the pulley, and do a little bit more algebra, and the signs get a little bit tricky because you have to make sure that you have that you're adding your tensions correctly there. All right, so now we can go to example 7.4, and here we're going to be able to address a question that would be incredibly hard to address with Newtonian mechanics. Technically it's possible, but you would have to have a pretty wild constraint. So we're going to look at a particle constrained to move in a cylinder, and we're going to define this is going to appear left-handed to you because I'm drawing it right-handed, although it doesn't really matter for this example. We're going to look at a particle which is confined to move on a cylinder. And here, we can always define it. So we will define its coordinates as in r, theta, and phi. So its position is always rho. So this has the cylinder has a radius rho. And then the angle can vary, and then the position, it has a height z. So then when we write down the kinetic energy is, let me choose a better color. The kinetic energy is 1/2 times the mass, and then this one, r dot, is 0 because it's held constant, although I'm going to write that just for completeness, and then rho phi dot quantity squared plus z dot quantity squared. So that's our kinetic energy. Of course, this is 0. And our potential energy is the mass times g times the height. I have switched this a little. Let's see. I have a slight correction. The particle is confined to a cylinder, but then it experiences a force kr. So it is a potential from this point. So that's going to look like a gravitational force around a heavy object. So then the potential is m times g times the, bear with me here. Sorry, not m, k. Our potential is k times m times the distance from the center. So that is going to be a rho squared plus z squared. And here, actually, the book called it r. I'm going to stick with rho because I'm halfway there. So then our Lagrangian is 1/2 m rho squared phi dot squared plus z dot squared minus k rho squared plus z squared. And then we have two variables, so we have to come up with equations for both. So we're going to look at partial L, partial phi, and that is 0. And partial L, partial phi dot is m rho squared phi dot. When we take the time derivative, that marker is not showing up. We take the time derivative and we add a dot there. Partial L, partial Z is equal to negative K Z and here I dropped this should have a 1/2. So that makes this negative kz when I take the derivative. And this is equal to, and that's gonna, then we have partial L, partial Z dot, which gives us mz dot. Take the second derivative, or sorry, take the time derivative, and I add another dot. So here we get this derivative is equal to that, so we get m rho squared phi dot is a constant. And here we get mz double dot is equal to negative kz. And you will recognize this as having a solution which describes simple harmonic oscillations. So in the z direction, you get simple harmonic oscillations. And in the phi direction, it is moving at some sort of constant speed. So here I could write this as z equals z naught cosine omega t plus phi naught, where omega squared is k over m. Okay, so here, now this problem was really artificial. Why would you have something with a force like this that is confined to a cylinder? But even though it's arbitrary and it has some weird constraints, when we use the Lagrangian formalism, we can actually solve the problem relatively easily, and we can write down the steps to do this. So first, we write down t and u, which gives us the Lagrangian. Then you want to choose what you want to be your generalized variables. Then you want to write the Lagrangian in terms of qi, which may take solving the equations. The way that I like to do it, if I have a constraint, is to do this step in the way, whatever way is easiest, write the constraint down, and then use algebra to solve for the rest of it. It adds a few steps, but it makes it a little bit more straightforward to do. And then you want to write down the Euler-Lagrange equations for the system. And then from there you have to solve it. So then you can do this with basically any type of problem. And we're going to go through a few more examples. All right, so we are going to move on to a variation on one of my favorite problems, the block sliding down an inclined plane. But we're going to add a complication, which if we were working with Newtonian mechanics and trying to solve these problems using a Newtonian approach, it would be pretty dang difficult. So we have a block sliding down a wedge. We are going to assume that the wedge is on a surface. It can slide without friction. Here we're going to neglect friction for the block sliding down the inclined plane or wedge. So we're going to define Q2 to be the distance between the mass and between the wedge and the wall, and Q1 is the distance down the block, and we are going to try to calculate how long it takes for the mass to reach the bottom. So then we can write and this is alpha. So we have, if we look at the, first of all, the kinetic energy of the big mass is easy. That is 1/2 m q2 dot. And then the position of mass of the little mass m is going to be, it's the velocity here plus the velocity there. So I am going to impose a coordinate system x and y. And this velocity is going to be q2 x hat, or sorry, q2, we really only care about the velocity. So I'm going to write this as q2 dot x hat plus, and then here we have q1 in this direction, and then the velocity of the mass relative to the wedge is q1, and then we have a cosine alpha x hat plus, let's see, minus q1 sine alpha y hat. And when we square this, and I dropped my dots, when we square this, it's the dot product of this with itself. That gives us q2 dot squared plus q1 dot squared cosine squared alpha plus 2q1 dot q2 dot cosine alpha plus q1 dot sine squared alpha. And this is equal to q2 dot squared plus q1 dot squared. Here what I'm doing is combining these two terms, so that gives me a q1 dot plus 2q1 dot q2 dot. So my kinetic energy for the little mass is 1/2 m q2 dot squared plus q1 dot squared plus, and here I dropped my cosine alpha after all of that, plus 2q1 dot q2 dot cosine alpha. And then the potential energy is, so we're going to define 0 as when this is at the top. So the potential energy is mgq1 sine alpha, so that the larger q1 is, the more negative, the lower the potential energy. That is saying that as the block goes down, it becomes, the potential energy decreases. That's the sign we want. And I'm going to explicitly list a U naught just because one of the things I think gets confusing about the way these problems are set up is that they don't always explain every decision. Like, all I care about is the potential energy has a term proportional to Q1 and mgq1 sine alpha. This is just some offset. All right, that means that my Lagrangian is 1/2 m plus m q2 dot squared plus 1/2 little m q1 dot squared plus m q1 dot q2 dot cosine alpha plus mg q1 sine alpha minus U naught. Here I'm going to do the derivatives at the same time. So let me just write up my Euler-Lagrange equations. partial L, partial Q1. Here I have that term only, so I get mg Q1, or sorry, mg sine alpha. And this is equal to the partial derivative with respect to Q1 dot. So I have an m, and then the time derivative of the partial derivative with respect to Q1 dot. So I have an m Q1 double dot plus m Q2 dot cosine alpha. And when I take the second derivative, I get another dot. So that's my first equation, partial L, partial Q2 is 0. And this is equal to the time derivative with the time derivative of partial L partial Q2 dot. So m plus m. I'm going to write just the derivative with respect to Q2 dot, and then I'm going to come back and take the second derivative. Excuse me. All right, and when I take the second derivative, I just add a dot on each of those Q dots. All right, and then so I have m plus m Q2 double dot. All right, and this actually tells us that here we can take this one, we get Q2 double dot equals m cosine alpha over m plus m Q1 double dot and that gives us something we can plug in here in order to solve for Q1. So we plug this in here and we get m Q1 double dot plus m squared cosine squared alpha over m plus m Q1 double dot and this here, I think I have a sign error. Yeah, here I made a sign error. So there's a sign difference there. So here I get Q1 double dot equals G sine alpha over 1 plus m, let's see, this was an m squared. Here, yeah, when I divided through by the m, this guy, let's see, that was okay. And then here, here to solve, I have m's everywhere, so I can get rid of one m. Okay, and then what we can do is look at our answer. You should always, you should get in the habit of doing this. Look at your answer and see if it makes sense. So when alpha is 90 degrees, then the block is just free falling. And what happens there is this is 0 and this, so cosine of alpha is 0, sine of alpha is 1, so Q1 double dot is just G, and we've defined Q1 so that it's positive pointing down in that case. That is what we want. When we have the big mass go to 0, so that this block, it can slide, but it doesn't take any energy to go to 0. We should see that this term drops out. So then we see Q1 reduces to, let's see, this should have a negative sign. Then this goes to 1 minus cosine squared of alpha, or sine squared of alpha, so we get G over sine, we're going to get, we get a G sine theta, G sine alpha, when we get the mass going to infinity, we want to look at what happens when the mass goes to infinity, when the big mass goes to infinity, this block will no longer slide. So we should see that Q2, this goes to infinity, so this term gets really, really small, and then Q2 double dot goes to 0. And when this goes to infinity, then this term goes away, and we get that Q1 double dot is just G sine theta. That is what we expect. When the mass is 0, the big mass is just pushed to the side. So here, and that one is actually left as a homework problem, but what you get is Q2 double dot is just negative cosine alpha Q1 double dot. So whatever this thing is doing, the block is just moving out of the way as the little mass slides down, and the mass is just free falling. Okay, so you can see how this would be almost intractable if you tried Newtonian mechanics, and it becomes much more reasonable if you use Lagrangian mechanics. Okay, so now we can move on to example 7.6, and this is a lovely example of something that you would never want to approach with Newtonian mechanics because it is simply complicated and hard. So what we're going to do is that we're going to have a loop which is spinning around in and out of the board, and we're going to put a little tiny bead on the loop. And we are going to describe the position of that bead. We're going to use polar coordinates. So this distance is r. And then we're going to describe the position of the bead with an angle theta. So this is actually not quite strictly polar coordinates because polar coordinates would have theta be up from the x-axis. We will put our x-axis here and our y-axis there. So this is not the same definition of theta as usual, but we're going to go with it to match the book. And then we're going to look at what happens so this is spinning like this. What does this bead do? So then we can describe the velocity of the bead as r theta dot in the theta hat direction. So here my, again, this is not quite polar coordinates because I always go in, well, because here this is theta hat. Theta hat is the direction of increasing theta. So, so increasing theta is that direction, r hat is that direction, and our velocity is r dot theta, or r theta dot phi hat, and then we've got, we have an angle of the loop overall, which is r sine theta times omega, the angular velocity of the loop of wire, phi hat. Okay, so the reason, so if you look here, this distance is r sine theta, and phi hat, phi is the angle relative to, of the x-axis, relative, is the angle of the x-axis relative to some origin, and so phi is going to rotate like that. So this is the velocity from it rotating in and out of the board is the radius of it going in and out of the board times the angular speed of it going in and out of the board. And our potential energy is mg r times 1 minus cosine theta. So here we're putting the 0 there. If we put the 0 of the potential there, then, well, you actually could just as well have put the 0 there, and then the potential would be mgr times negative cosine of theta, because you're looking at how far it is below the x-axis. We are following the book, but at any rate, this term is a constant, so when we take the derivatives for the Lagrangian, it's going to cancel out. So we need, for our Lagrangian, we get 1/2 m this mess squared, so I get an r squared theta dot squared plus omega squared. Well, I can write this different ways. I'm going to actually use, for omega, this guy is phi dot, so we will use phi dot squared sine squared theta. And then our Lagrangian is t minus u, so this is 1/2 m r squared theta dot squared plus phi dot squared sine squared theta. And then I'm going to have a plus mgr cosine theta minus whatever minus u naught. We're not going to worry about what it is, because when we take the derivatives, it goes away. Now, our Euler-Lagrange equations are partial L, partial Qi equals d dt partial L partial Qi dot. And here, because this is a constant, even though, so at first glance, it might look like you have two variables, you actually only have one. And now we're going to do partial L, partial theta. So here I've got a theta there and a theta there. So I get negative 2 times, so I get a 2 from taking the derivative there, and I have a half there. So m, I believe I dropped a squared. No, I did not. So positive, bear with me here. We'll just do it step by step. 1/2 mr squared phi dot squared times 2 sine theta cosine theta. So I always, when thinking about the sign, okay, sine starts at 0 and it goes up, so I want the derivative to be positive, so I don't flip the sign there. And then I have to take the derivative of this term with respect to theta. So I get a negative mgr sine theta. Partial L, partial theta dot. Here I've got 1 theta dot, so I get an mr squared theta dot. And I'm going to take the time derivative and I add an extra dot. So my equation here, this has to equal that. So here I have a negative mgr sine theta plus mr squared phi dot squared sine theta cosine theta. And I have m's everywhere, and I have at least 1 r in every term. So I'm going to cancel out 1 r from each term. And then I'm going to divide through by r. So that's going to leave me with that. So I can rearrange this. I have here theta, and actually I'm going to move it over here so that I can erase some of this. I have theta double dot equals, I'm going to pull a sine theta out in front, negative g over r plus phi dot squared cosine theta times sine theta. All right, this thing cannot be solved analytically, but we can actually evaluate the properties of these solutions. Okay, so then we can look here and see if there are equilibrium positions. If there are equilibrium positions, this thing is equal to 0. So in that case, we get negative g, sine, this guy goes, so if you're worried about this thing going to 0, you will get that when this mess in the parentheses goes to 0. So this actually, these two terms are equal in that case. Ooh, it never erases when you want it to erase, but it doesn't erase very well but it erases when you don't want it to erase. Okay, so here, now this we also call omega squared. This is set by how fast this is rotating. So you will get equilibrium positions if cosine of theta is equal to, you will get equilibrium positions where cosine of theta is equal to g r over omega squared. So you will only get equilibrium positions if omega squared is greater than g over r. If omega squared is less than g over r, then this thing is, if you only get, if omega squared is very large, then this goes to 0 and cosine theta is defined. And then if this is very small, you still need to have any equilibrium. Now, this is in SI units. So if you had something very slow, you would need to have a larger r to make sure that this cosine theta is going to 0. Now, if you're going very fast, the cosine theta is going to go to 0. Cosine theta is 0 when theta is 90 degrees, or plus or minus 90 degrees. So that's telling you that when you go very fast, the equilibrium position is there. The positions are there and there. So you'll have two, and they're on opposite sides. And then we can look at what happens. So if we want to look at what happens when you have small theta, so you're going slow, the slower you're going, the larger cosine theta, so the smaller theta is. If we want to, so you can get equilibrium positions where they're slightly off center, but not as far out as 90 degrees. So we will look at the small angle approximations. When you have a small angle, this term is roughly equal to 1, and this term is roughly equal to theta. So our small angle approximation is this, and this just gives us oscillatory motion. So if you are going slow, the bead is going to oscillate back and forth up here. Now the second equilibrium point, if you're going very slow, is there. So if you're going very slow, cosine of theta is 0. Cosine of theta can be 0 when, cosine of theta is close to 1. Cosine of theta is close to 1 when you're on the bottom of the ring and when your bead is on the top of the ring. So then if you want to look at, so the bottom of, if you are at the bottom of the ring and you have slight deviations, then what we can do is we can look at one larger expansion of this. Here I'm flying without a net. My notes didn't address this. So bear with me. This is now 1 minus theta squared over 2. That's the next highest expansion of that. And this is theta minus theta cubed over 6. So if we want to keep one higher expansion, theta double dot is roughly G over R plus phi dot squared. Now, our lowest non-zero term is theta of order theta. The next lowest term we can't get, so this will make a term of order theta. This will make a term of order theta to the third, and this will make a term of order theta to the third. So then we have negative g over r, and the next lowest term we have is this times that. So we get a negative, hang on. So we're going to get a phi dot squared times negative theta cubed over 2. And then we're going to get a positive g over r theta cubed over 6. So our next highest term, negative g over r plus phi dot squared theta plus, I'm going to pull out the, a theta cubed over 6, and that leaves me with a g over r minus 3 phi dot squared. So now, if I have, so I have to have phi dot squared greater than g over r to have the equilibrium position. So this is negative. My second derivative is going to be negative if this term is positive. Here I'm going to get, if I'm at the bottom, because I'm close to theta equals 0, this is going to be negative if I am at the bottom. If I'm on this side, it's going to push it this way. If I'm on this side, it's going to push it this way. Whereas up here, if I'm on this side, it's going to push it. If I'm on this side, it's going to push it more that way. So this one is an unstable equilibrium point. So the top is always unstable, and the bottom can be unstable depending on how fast this is spinning. And the red points are stable. The points off to the side are stable if you have them. Okay, so now we're going to look at these equilibrium positions, and we are going to use my best friend, a Taylor series. So here, first of all, we're going to define theta naught. Let's see, I should have had, yeah. We're gonna go back, sorry, we're not going to go around 0. We're going to go back to this guy, and we're going to define theta naught to be the one where this is equal to 0. So we're going to define that as the equilibrium position. There's nothing in the calculus that I'm going to do that is anything new conceptually, but I want to show you how it works because you learned this in a math class, kind of detached from a physical problem, and now it's relevant. So we're going to say negative g over r equals, positive g over r equals phi dot squared cosine theta naught. And then what that means is that cosine theta naught equals g over r. I dropped, I didn't. Equals g over r phi dot squared. You can solve that in terms of theta, but I don't know that it matters. Now, we're going to use our next highest term in the Taylor series. So cosine of, well, let me actually just refresh your memory. For a Taylor series, f of x is equal to f of x naught plus f prime, the first derivative of x naught, times x minus x naught plus f double prime, the second derivative evaluated at x naught, times 1/2 or 1 over n factorial x minus x naught quantity squared, and then higher order terms. And the only thing that we're going to look at here is up to second order. We're going to take the first two non-zero terms. So let me just real quickly, if f of x is, let me make a table, f of x is f of theta is cosine of theta, or f of theta is sine of theta, f prime of theta and f double prime of theta. So cosine of theta, negative sine theta, and then negative cosine theta. And sine theta, first derivative is cosine theta, second derivative is negative sine theta. So, and we're going to call this term epsilon, so that we're not having to write, we're going to call x is epsilon. We'll just leave it as right here. We're going to write theta equals theta naught plus epsilon. So we're going to be expanding in terms of, so this is x epsilon. We're going to be expanding in terms of the difference between this and epsilon and theta naught. So cosine theta is approximately cosine theta naught minus sine theta naught times epsilon. First the function and then its first derivative. Sine theta is approximately sine theta naught, and then plus epsilon times cosine theta naught, and then higher order terms. So then we can plug that back in here, and theta double dot is approximately equal to, our negative g over r term is not modified at all, but here we have our phi dot squared, and then this is cosine theta naught minus epsilon sine theta naught. And then this is multiplied by sine theta naught plus epsilon cosine theta naught. And we are only going to keep terms of order epsilon. And we're going to note here that this is epsilon double dot, because this term is a constant, so we take the first derivative and we get epsilon dot, and the second derivative and we get epsilon double dot. And Now, when we multiply all of this out, so here we get negative G over R plus omega naught squared cosine theta naught. Of course, this is equal to 0, because that's the whole point. And then we get a plus epsilon and here I get this term times the sine squared term, because I need order 1 in epsilon. So I have a minus epsilon phi dot squared sine squared theta naught. And then here then I am left. So this term, I would get the sine theta naught term. But the sine theta naught term, because this stuff is 0, that term goes away. And then I am left with terms of order epsilon squared. So I get something which has epsilon double dot is equal to negative epsilon omega squared sine squared theta. So I can identify here that I actually have, so this is simple harmonic oscillations near the bottom, or sorry, near the edges, and I get a different oscillation frequency, which works out to be capital Omega is phi dot squared minus G over omega R quantity squared. All right, so then we're going to talk about generalized momenta and ignorable coordinates. And these terms are used. Don't worry too much, because if you what I don't like about the way this is often covered is that it makes it seem like you have to have some great insight and see everything before you solve the problem. And anytime you have to come up with something clever and like understand the problem before you, and its solutions before you solve it, it's intimidating and it's unlikely to work. But you don't actually have to. So think of this more as a way to look at things when you get certain answers. So our Euler-Lagrange equations are partial L, partial Qi, equals d dt partial L partial Qi dot. So we have introduced the concepts of generalized momenta and generalized forces. So this is our generalized force, Fi. And then this says that the generalized force is the time derivative of the for a given coordinate is the generalized momentum of that coordinate. So if the force is equal to, the generalized force is equal to 0, then the Qi in that particular case is constant. So you say that the QI is ignorable or cyclic. Those are those are two terms that are used. So if we take an example, a particle in a projectile motion in gravity near the Earth, the Lagrangian is 1/2 m x dot squared plus y dot squared plus z dot squared minus mgz. So this is putting z on the surface of the Earth, and then it's the distance from the surface of the Earth, and x and y are relative to the Earth, but on the surface. And when you do partial L, partial x, this is 0, which means that mx double dot is 0 or x dot is constant, and you get something similar for y dot. And you only have one term, which is where the momentum is not constant, and there you get mz double dot equals negative mg is equal to negative mg. So what you typically, what the book says, and then let me expound upon my opinion. The book says that you want to choose coordinates where as many as possible are ignorable. I think that this is a judgment call. It means if you choose more coordinates that are ignorable, then it makes the problem easier. You can, when you apply Euler-Lagrange equations, then the answer falls out pretty easily. Sometimes the problem is only tractable that way. But what you're trying to optimize is the amount of time you put into the problem. So sometimes, especially if you're, say, going to proceed and solve the problem numerically, or you really want to have it in Cartesian coordinates because that's the way that it's easiest to work with the output, sometimes don't worry about it. Make a judgment call. But there is something deep in this, that every time you have one of these ignorable coordinates, every time corresponds to some type of symmetry. So every continuous symmetry of the action has a corresponding conservation law. This is the way that it's worded. This is something called Noether's theorem, after Emmy Noether, who was a famous mathematician. Well, not as famous as she should have been. She was a genius and didn't get enough credit for her work. And so here, when we have an ignorable coordinate, so the Lagrangian does not depend on x and y, you have conservation of momentum. And every time you have one of those symmetries, you will have a conservation law. Now, the next section, the conclusion, it's actually, the way this chapter is structured is a little weird. There's a conclusion, and then there's 4 additional sections that talk about other details, and I'm going to go through those additional sections. So that conclusion is not really a conclusion, I think, and some of it goes back through things that have been said 45 times already in this lecture, so I'm not going to go through them in detail. The one thing that is mentioned is that is useful is that this doesn't naturally work with magnetism, but it can in fact be expanded to include magnetism. Now magnetism of course works differently than the other forces because the force depends on the velocity, and that's why the Lagrangian formalism, as we have covered it just now, doesn't easily cover magnetism. And then you can actually also extend it to include dissipative forces, those which are not conserved, but it is complicated and it is also probably not worth it in many cases. So a lot of times when we talk about Lagrangian formalism, the most useful thing to do with it is to consider problems when you have no dissipative forces, or when that is actually a pretty good approximation of the system. So we're going to come back to, this is section 7.8, which is about conservation laws. It's listed as an asterisk, which means that it's not strictly speaking necessary, but it's useful, I think, for thinking about how the Lagrangian formalism is useful, because you actually can use it to answer some deep questions. And so, and this is because of Noether's theorem. All right, so we're going to consider a system which is isolated, where the potential, so the potential is translationally invariant. So what that means is the potential energy, if you have R plus epsilon, this is, so some displacement, the potential is the same. So for instance, if you consider a system without gravity, or this could be, well, moving in the X or Y direction, but not the Z direction along Earth, so not perpendicular. So this is translationally invariant, and then we'll look at what that means. So if we have, under this type of variation, our change, so we're slightly shifting the system translationally, then the change in the potential energy is 0, and the change in the kinetic energy is then also 0, because you only depend on the coordinates, on the second derivatives of the coordinates, and the second derivatives are not explicitly dependent on the position. So that means that under this type of translation, the Lagrangian itself is translationally invariant. And that then means that if you take we're going to let this epsilon be moving in one bit in every direction, just because we're choosing this arbitrarily, and it will make everything a lot easier to write down if we don't choose arbitrary displacements. So then this change in the Lagrangian is a small, so that is going to give you epsilon dotted with, well, let me actually write this the way the book writes it rather than trying to come up with clever terminology. So in this case, that we move each variable by the same amount epsilon, you have a small change in x1 plus a small change. Let me actually leave this as q1, because we'll leave them as arbitrary variables, q2. So the Lagrangian will be shifted by however much each of these changes. And then this implies that, so this I can write as epsilon plus the derivatives times the derivatives of the sum of the qi. Let me write that neatly, legibly. And of course this, so that's equal to 0, which implies that the sum itself is equal to 0 because epsilon is arbitrary. And this is simply the time derivative of the qi dot which is the time derivative of the sum of all of the generalized momenta. But of course, this has to then individually be true because you can arbitrarily choose different sets of variables. So this tells you that the time derivatives of the momenta for an isolated system, well, the time derivative of the sum of the momenta for all of the particles for an isolated system is in fact 0. So you could have written this, I wrote this as the sum over the variables. The book wrote this as the sum over all of the different coordinates, or sorry, all of the different particles. You actually could write over all of the different particles or all of the different variables. So that when the book did this to address a multi-particle system, so when you shift the entire system, you're moving all of the particles in the same direction. You're not changing their potentials relative to each other. So this, instead of being a sum over, you're just picking one of the observables. So this would be qi of the alphth particle and this says that the sum of all momenta over in one direction has to be 0. So in each direction, the total momentum is conserved. So then we can look at the time derivative of the Lagrangian. So we're going to assume that there are no explicit changes in the potential due to time. So d dt of the Lagrangian is going to be the sum over all of the generalized variables of the derivative of the Lagrangian with respect to the qi times qi dot. So this is dqi dt. So when we multiply these, we get a time dependence. And then we will get plus the partial derivative of the Lagrangian with respect to the qi dot, partial qi dot, or sorry, times the time derivative of the qi dot, and the time derivative of the qi dot is qi double dot, plus any explicit time dependence of the Lagrangian. So let me actually change colors to highlight things. Partial L, partial QI is, through the Euler-Lagrange equations, ddt, partial L, partial QI dot, which is d dt of the ith generalized momentum. So this is pi dot, and this, this term is simply pi. So we can rewrite this right here as d dt of the Lagrangian is equal to the sum over all generalized variables. I'm going to move the sum here and put a large parentheses here. This is pi dot times qi dot plus pi times qi double dot plus the partial L partial t, the derivative with respect to the explicit time dependence. Now here we can be a little clever and note that this is what you get if you apply the product rule to pi times qi. So this, sorry, pi times qi dot. So this is the time derivative of the sum over all pi qi dot plus this derivative. So if there is no explicit time dependence, then this guy simply goes to 0. And we can write that so we can write partial L, not partial, full derivative, d dt of the Lagrangian is equal to d dt of the sum over I pi qi dot, and we can put this over on the same side and say 0 equals d dt of the sum over I pi qi dot minus the Lagrangian. So then we're going to define this mess in here, the pi qi dot minus the Lagrangian as something called the Hamiltonian. And in many cases, the Hamiltonian is the total energy in the system. So if we do a simple example very quickly, we have a particle of mass m, and in that case, the Lagrangian is 1/2 m qi, we'll just do one dimension, 1/2 m qi dot squared. Or sorry, we'll do Cartesian coordinates because I don't want to mess with non-Cartesian. I'm just making an example up on the fly, minus the potential. So then the Hamiltonian in that case is we will do, that one is, that turns out to be m times the qi dot squared minus 1/2 m times the qi dot squared plus u, or 1/2 m times the sum of the squares of the time derivatives of the coordinates plus u. So in many cases, the Hamiltonian is the energy. So we're going to look at this, and so here I've rewritten the Hamiltonian, and the definition of the Hamiltonian, and we're going to look at this and try to derive this. So we're going to look at, for alpha particles, what I mean by that is that I have 1 through alpha particles in the system. The derivative is the sum, the derivative of the position of the alpha particle is the sum over all of the generalized coordinates, partial r alpha, partial qi, times qi dot. So I take the derivative of the position with respect to the coordinate and multiply by the time derivative of the coordinate. And then I can look at the square of this. So I'm going to dot it with itself. And this is the sum. I'm going to have 2 indices, I and j, of partial r alpha, partial q k, I have a j and a k and a q. Oh, sorry, I have I and j. I want I and j, and here qi, qk. This notation, where I'm not writing 2 sums, that indicates a double sum. So then my kinetic energy is 1/2 the sum over alpha, j, and k. I don't know why I switched from I and j to j and k there, but my notes do it. So I will do it too. It's an arbitrary index, so it doesn't really matter. That's a j, and that's a k. Now, the momentum in the system is the generalized momentum. So the ith momentum is the derivative of the Lagrangian with respect to qi dot. And this, because the Lagrangian is the potential, or sorry, the kinetic energy minus the potential, and the potential has no dependence on the qi dot. This is the mi, the generalized momentum. And then this is here, if I look at this, I am going to take the derivative of this. So, this is why it was important that I did J and K, because now I'm going to take the derivative of this with respect to the ith momentum, and I will only have a non-zero term here, where either this or that is the ith qi dot. So I am going to choose the case where k, where k is equal to I. So one of these sums collapses. So here, because we were only considering one particle, I have the m alpha and partial r alpha, partial q j, partial r alpha, partial q I, q j dot. All right. Then I can look at this quantity, pi qi dot, for a single particle is the mass So here I have used that the pi is this expression. And then by comparison with this, I can see that this is in fact 2t. So then I can come back here, and this is 2t minus t plus u, or t plus u. So if we have, so in this case, the Hamiltonian is exactly what we are familiar with as the energy. And so if we use Cartesian coordinates, the generalized coordinates are then time independent. You don't change the definition of the time dependence. So the Hamiltonian is the total energy. So time independent coordinates then implies that, a time independent Lagrangian then implies energy conservation. Now you can always write the Lagrangian in terms of Cartesian coordinates, because you can choose whichever coordinates you want. So as long as the Lagrangian does not have any explicit time dependence, then you have energy conservation. So we're going to talk about how we expand the definition of the Lagrangian in order to work for the magnetic force. So we're going to define the Lagrangian as the function L for which the equations of motion are given by the Euler-Lagrange equation. Partial L, partial Qi equals d dt, partial L, partial Qi dot. This definition is a little bit circular. But then when we come back to how we add the magnetic force, we're going to look for the function for which this works and see how we have to modify what we have done so far. Now, Lagrangians are not unique. So if we have a function f and partial f, we'll just consider the variable to be x instead of some generic variable. Partial f partial x equals d dt partial f partial x dot. An example of this is x dot. So if we have a function like that, we can always add that term to our Lagrangian, and it will also be a solution of the Lagrangian. So we can say L prime is L plus F. L prime is also a perfectly valid Lagrangian for that system. So this is actually kind of deep. So now we're going to come back and try to figure out how we modify our Lagrangian to make it work for a magnetic field. So let's start with what we know from electricity and magnetism. Mr double dot is Q E plus R dot crossed with B. So this is a differential equation. And what we're going to do is that we're going to try to spot the Lagrangian. And we're going to write this as, we're going to note that we have a vector, so our net field, we can write our net field as negative gradient of the potential minus partial A, partial T, where A is the vector field. And so the net electric field is this. So the electric field has a component from the gradient of the potential and also a time derivative of the vector field. So a changing magnetic field leads to an electric field. And then we're going to test this Lagrangian. This looks familiar. This is just 1/2 mv squared. Minus Q V minus R dot A. Really what we're going to do here is show that this actually works. Now this looks like, this should be QV R dot A. So this is just our potential energy from our electric field. So this is 1/2 m x dot squared plus y dot squared plus z dot squared minus Q V minus x dot AX. We're going to use Cartesian coordinates here. And then if you can write it in Cartesian coordinates, you can write it in other coordinates. And we will see, we want to check that this reproduces Newton's second law for both an electric and a magnetic field. So now we're going to take this and try to apply the Euler-Lagrange equations. So I'll change color just to make the board prettier. Partial L, partial X. We're going to focus on the X version. So there's X dependence in principle in these three terms. So we get negative Q, partial V, partial X, plus, well, let me leave the negative sign. Let me follow the book, not be a rogue. And then we have partial derivatives with respect to X for each of these terms. And then we can take partial L, partial X dot, equals, I put the parentheses here. And now here we have mx double dot. Nope, I'm moving one step too fast. Mx dot, because I'm going to come back and take the time derivative. And there's no explicit x dot, y dot, or z dot dependence in the vector field. So we will have plus q a x. And then we need to take the time derivative. And now the time derivative is not as simple as just adding a dot. Because now the first term, I just add a dot. But in the second term, I can have x, y, and z dependence in addition to having an explicit time dependence. So when I take the time derivative of the, this thing, I have partial ax, partial x, partial x, partial, no, dx dt, plus partial ax, partial y, dy dt, plus partial a y, partial a x, partial z, d z dt, plus partial a x, partial t. And then I can take, so this equals that, and I am going to move all of this over here. So I get mx double dot equals negative q. Now let me track terms really quickly. So I'm going, and I don't want to rewrite all of this. Normally, pedagogically, I would write a lot more. That's kind of painful. And I'm going to actually make some, so this is x dot. I like writing it in terms of derivatives when I'm doing this step because it just makes it much more explicit. Okay, so this term just comes down for the ride. And then I am going to collect terms that have, so let me actually, I'm going to collect terms that have x dots and y dots. So this guy is actually, these ones are positive. So I'm going to, because this negative sign comes in, so I'm going to write plus q x dot partial ax partial x, leave a spot, plus q y dot partial ay partial x and then I'm going plus q z dot partial a z partial x. Oof. This is barely fitting, so we're going to be a little creative. I'm going to squeeze this in just a little bit there. Okay, so I have my partials with respect to x. Ah, yes, and I actually need to squeeze in a term here. What I'm going to do is that I am going to put all of the terms from this in this color. So now, here, I have a partial ax partial t. Now, my x dot term is partial, let's see, let's see, this should be, okay, so this is the term from here, and then, no, this is the term from here, and then this term, we bring it on the other side, and it becomes partial ax partial x. So these two terms cancel out. Yay, I love it when things cancel because it means that they are getting easier. All right. Then our y dot terms, this becomes negative. So I have a negative partial ax partial y. And then here, this is negative as well. So I have a partial ax, partial z. So then we would have for y, we would have similar terms. And then for y, you would change y and x, which would flip the sign of this term. And here, you would flip the y and x, and you would end up with this term. And we can also note, so this, from electricity and magnetism, this term is Bz. This term is a negative By. So this simplifies to, running out of space here, mx double dot equals Q times the electric field, because this is the electric field, plus y dot Bz minus z dot By. And then we would get similar terms for y and z. So we can see that, in fact, if we take as our Lagrangian, instead of the kinetic energy alone, we add this extra term for the electric and for the electric potential and the magnetic field. So you add an effective vector potential for the magnetic field. This works. So then, if we have this Lagrangian instead, let's look at the momentum in the x direction. This is partial L, partial x dot, and this is then mx dot plus q ax. So you have an extra term from the momentum, and we can look at the other directions, and our momentum is then mv plus q times this vector potential. And if we are willing to accept that as a consequence, then we can get the Lagrangian framework to work for electricity and magnetism. And this approach is extremely important for quantum mechanical descriptions of electricity and magnetism. So now we're going to move on to the last section, which I really don't think should be relegated to the last section, because you can go pretty far without knowing the Lagrangian for magnetic force and classical mechanics and thinking about conservation laws. But this is one thing I've actually used. That's Lagrange multipliers and force constraints. So we have so far talked about generalized coordinates so that you only use as many coordinates as you really need to describe the problem. And when you do that, when you use the least number of coordinates, you end up with a simple equation. You can solve for the equations of motion faster, but sometimes you want more than the equations of motion. For instance, if you are designing a roller coaster, you actually want to know the forces that are required to keep the roller coaster on the track. So you can do that with Lagrange multipliers, things like that will give you things like when you're talking about an Atwood machine, you can get the tensions in the string. So here you basically don't worry about having chosen the most clever set of coordinates, you're going to use more parameters and use Lagrange multipliers to handle the constraints. Now, the types of constraints that we can handle with Lagrange multipliers are when you can write the constraint as a function of the variables, and write say some function is a constant. So you can say that, for instance, if we talk about the Atwood machine, then the length of the string, the distance between, if you go around the string, the distance between the two masses is a constant. You can solve that type of problem with it. You can solve a problem where you've got, for instance, we talked about a bead going around in a circle. You can solve that type of problem because you can write the radius as a constant. But what you cannot do is something where it's an inequality. So you could not have something where the normal force has to be greater than or equal to 0. It can't be negative. You have to be able to describe it in this form. And this allows for constraints, but we note that the constraints, so if you consider the Atwood machine, the constraints are coupled. So we are going to look at, so remember that our action is the integral of the Lagrangian with respect to time. So a slight change in the action is going to be, we're going to allow two variables, x and y, and posit that it can be generalized to more variables, but a good physicist is a lazy physicist, so we're not going to write out all of the variables. They wouldn't even really fit on this board that well anyways. So we can write this as partial L, partial x minus d dt, partial L, partial x dot, small change in x, dt, plus that should not look like some sort of special character, so we'll rewrite it. D dt, partial L, partial y dot, small change in y, dt. Now what's different here is that these are not 0, these are coupled together. So we will choose small change in f has to equal 0 because this is a constant, and that is partial f partial x times a small change in x plus partial f partial y times a small change in y. And we will choose lambda, which can be a function of t, such that this is true. And then partial y partial x plus lambda f partial f partial x. So here, so what we're going to do, because this has to equal 0, we're going to add that term to both of these. And so here we have delta S is partial L partial x minus lambda partial x F minus D dt partial L partial x dot delta x delta t plus the exact same thing delta y delta t. Now, whereas here, because we had a constraint that connected these two, we couldn't just say they have to be independently zero. But now that we are writing this, and I should have that, just by convention, it actually doesn't matter if you change the sign of lambda. Now, all of these, this only depends on y, and that only depends on x. And so they have to be independently true. So then you have a modified Euler-Lagrange equation using Lagrange multipliers so that you get this extra term. And so the two key parts are you have this if you can write your constraint as this. Now, when you take these derivatives, what you're going to, you take these derivatives so that you can get the equation. You may need to use your equation of constraint again. And then you will get an equation of motion, which has, you'll get equations of motions that have x double dot, y double dot, and lambda, and you can, in principle, solve for all three. Now, we've derived this for one constraint, so if you have one equation that constrains this, you would have this. If you had two equations that constrain it, you could add an extra term. So this should not be a y, this is an L. So you could have partial L partial x plus lambda 1 partial f 1 partial x plus lambda 2 partial f2 partial x equals d dt partial L partial x dot. So that would give you, if you had two equations, and you can expand for more, if you had more equations of constraint. So if you have, so let's take the first case. You got you have an Atwood machine. You have in the case of the Atwood machine, which is the example that we are going to do next, M1, M2. This one is y. This one is x. In the case of a massless string, then the tension is the same throughout. So you have one constraint. You have the and you have the length of the string. It gives you one constraint. So in that case, you would get three variables and three unknowns. You have x, y, and the tension in the string. So you would get all, because you have three equations and three unknowns, you can solve that problem. All right, so we will move on to that example. So in this case, we will write our Lagrangian as 1/2 m x dot squared plus, 1/2 m1 x dot squared plus 1/2 m2 y dot squared plus m1 gx plus m2 gy, and for good measure, just so that we remember that it's there, I'm going to write a minus u naught. So you can actually write the potential. If we put the 0 here, you could write it all sorts of different ways, but if we put the 0 there, this potential happens to be 0. We can then write our equation of constraint as f of x and y equals x plus y plus pi times the radius, a, equals the length of the string. All right, so then we will look at partial L, excuse me, partial x, which is m1g, and then partial f, partial x, is equal to 1. d dt of partial L, partial x dot, is going to give us mx double dot. We can write similar equations for y. This is an m2. So we plug this in. We get m1g plus lambda equals mx double dot m2g plus lambda equals m2y double dot. And then we're also going to need our, we're going to use our equation of constraint as follows. We can take, when we take the derivative, the time derivative of f, we get x dot plus y dot equals 0. We can take the second derivative, and we find out that the second derivative of x is equal in sign, but equal in magnitude and opposite in sign to y. We could have figured that out without the equation of constraint, but I always like to do things, I like to start with what I write down and see if it makes sense to me, because then I can be more certain that I have written the right things down. It's a way of checking, even though it's kind of redundant, it's a way of checking to make sure that what I have done is correct. Okay, so I am going to rearrange this, and I get g plus lambda over m1 equals x double dot, and g plus lambda over m2 equals y double dot. And this is equal to negative x double dot. So I can get, now there's a whole bunch of different mathematical tricks. Let's see, I could take this, what I'm going to do to get rid of the x's and y, or sorry, get rid of the lambda, is that I'm going to take this equation and subtract off that equation. So I get m1 minus m2 g equals, let's see, this one minus that one. This is equal to m1 minus m2, but then you get another plus sign when you use the x double dot is equal to negative y double dot. So I get x double dot equals m1 minus m2 over m1 plus m2 times g. I can use this equation and get y double dot is equal in magnitude or opposite in sign here, that tells you that if M2 is larger than M1, y is going to increase. If M2 is less than M1, y is going to decrease. And vice versa for x. Now we have to solve for lambda. There's a few ways that we could do this. I guess, how is it I want to do this? I'm going to add these two. I didn't actually end up using this. I'm going to add these two equations. I have things in my notes where I did it, but there are a few things I like better than living dangerously, so I'm going to record a video that I'm going to post on the internet without my notes. So if I take the sum of these two, M1 plus M2 times G plus 2 lambda equals M1 plus M2. Actually, I'm going to use so M1 minus M2 x double dot, and then I can use this. All right, so I'm going to move that up here. So M1 minus M, so I have M1 plus M2G plus 2 lambda equals M1 minus M2. Actually here, let me go ahead and just solve for lambda, and then we'll have some ugly algebra. So lambda is 1/2 negative M1 plus M2 G plus M1 minus M2 times x double dot, which is M1 minus M2, so we have that squared, M1 plus M2 times G, so this is G over 2 over M1 plus M2, and then this is M1 squared minus 2 M1 M2 plus M2 squared minus M1 squared minus, you can't read the squared right there. It's a squared. Minus M1 squared minus 2 M1 M2. Okay. Lambda is then equal to 2 negative 2G M1 M2 over M1 plus M2. And then we get to the interpretation of this lambda. So in this case, so when you write this form of the Euler-Lagrange equations, then this is your force of constraint, and this gives you, if it is in Cartesian coordinates, this is your total force. And if there's typically no position dependence on the velocities and no position dependence on the kinetic energy, So this is just negative partial u partial x. And this is the force from the constraint. And this is the force other than the constraint. So the total force is equal to the force not from the constraint plus the force due to the constraint. So by doing this, then we can interpret this as the tension in the string, which is in fact causing the constraint.